Welcome to NALLA Reddy Education Society's group of institutions, integrated campus, Hyderabad, structural engineering, one that is reinforced cement concrete. I am Dr. A. Mahesh Babu, Professor, Department of Civil Engineering. In last class, I explained about pre-stressed concrete structure, plain concrete structures. In today's class, I will explain RCC, reinforced cement concrete. This is one of the very important topic. Try to understand. If you understand these concepts, it's very easy to understand coming topic. RCC, generally we'll call it as RCC. What is RCC? Reinforced cement concrete. See, by name itself, you know, reinforced cement concrete means what are the material used in the reinforced cement concrete? Cement, sand, aggregates, water. The full form of RCC is, I said, reinforced cement concrete. It is a mixture of, as said, cement, coarse aggregates and fine aggregate, that is sand, and reinforced with steel bars. See, this is the difference between plain cement concrete and over reinforced cement concrete. It is generally a concrete which contains steel bars. This steel bars, also known as rebars or reinforcement bars. All the words or sentences are same: steel bars, rebars, or reinforcement bars. Technically, we'll call them reinforcement or steel. Okay. The combination of RCC works very well. The PCC with reinforcement works very well. That is very strong. In compression, RCC is strong in compression and tension because of steel. So basically, concrete is very strong in compression and is very strong, and steel is very strong in tension. So this is the very important point for us. Just I wish underline this. The combination of RCC works well. Why? Because a concrete is very strong here, very strong in compression. See, this is a very basic, important and very important point. This is one of the very important concept in RCC. And why we are using steel here? We will use steel use here because very strong in tension. Okay, that I will show you in figure. Compared to other material, it is very easy to produce at site, also inexpensive. See, our cement, aggregates, and all reinforcement, it is easy to produce at the site. And in next slide, concrete is good in resisting compressive stress. but very weak in resisting tensile stresses. See, whenever forces acting on a structural element or any structure, definitely acting towards structure, you will get that element, that structure is resisting compressive stress, and but very weak in resisting tensile stress. That's why we will provide reinforcement in the concrete wherever tensile stress is expected. Wherever tensile stress expected, we'll provide reinforcement. The best reinforcing material is steel. Why? Because its tensile strength is very high, and one important condition point is that the bond between steel and concrete is good. See, if we look at reinforcing material, that is steel, and strength is high, and very important point is the bond between steel and concrete is good, and elastic modulus of steel is quite high compared to concrete. The force developed in steel is high. So this is also one of the important point. Here, these are very basic concepts of RCC. What is that? Basically, concrete is very strong in compression and very weak in tensile stress. But reinforcement is very strong in tensile stresses, to take care of tensile stresses. So that's why we will provide tensile reinforcement. Okay, and one more important point is why we are going to use steel in the RCC, because there is a good bond between steel and concrete. Wherever tensile stresses develop, will provide reinforcement. Just you observe this, watch this video, how compressive tensile stresses developed and why we are going to provide reinforcement.
G'day, welcome back to BuildSim, and what I want to show you today in this video is the strength and weakness of concrete and steel and how we use them together as reinforced concrete to provide or to form a very strong structural member of our building. So essentially, this is our slab of concrete, and concrete is very strong when it's compressed or pushed together. So think about a force being pushed along the line of these arrows, pushing the concrete together. The concrete's going to stand up pretty well. It's not going to want to crack or anything, and it's very strong in compression. However, if we were to reverse the situation and try and pull the concrete apart, then the concrete's going to break reasonably easy. So concrete is very strong in compression, very weak in tension. Steel, like our reinforcing rod, however, is the opposite. It is incredibly strong in tension. So think about a tug of war with a steel
reinforcement.
Rod.
This is reinforcement.
Cars to the rod. You need a fair bit of force to cause any damage to the rod. So steel is very strong in tension. However, if we were to try and compress it, it would very quickly deform and buckle and get out of shape. So steel has the exact opposite properties as our concrete. So that's why we can form them together. But the thing is, our concrete slab's just sitting there. How is it ever going to be placed under compression or tension? So what happens, especially with suspended slabs, if the slab's supported on both ends, such as this one, and then there's a load placed in the middle, and that could be the self-weight of the concrete or any live loads or dead loads that you're going to put on top of it, then what's trying to happen is that the slab is being pushed or trying to be pushed into that shape. So what that does is, because it's now a concave shape, the top of the slab is actually been compressed by the load, and the bottom half of the slab is now in tension because it's actually been made longer. So this is where the structural engineers come into play, and this is how they work out where they're going to place their reinforcement. So we need to place reinforcement in the areas of the slab that are going to be placed under tension.
See, bottom is bending moment. This is simply supported beam, WL square by 8, your bending moment curve, tensile stresses will develop at the bottom. That's why we will provide steel reinforcement at bottom of the beam section.
So in this case, the bottom half of the slab is going to be in tension. So we need to put our reinforcement in the bottom half of the slab. All right, not right on the bottom because we have to allow for our cover, and not right to the ends again for cover, but in the bottom half of the slab. Now, as I said before, this is where structural engineers make their money, because there's going to be lots of different situations where we're going to have different loads and different scenarios. So in this instance, such as a cantilever, we've got a load down in the middle, and again, we're going to have the self-weight of the slab plus anything else we're going to put out here on this end of the slab, causing a load out here. So there's actually going to be a bend over that support and a bend in here as well. So this is where our structural engineers can advise us where to place our steel and what size it needs to be. So hopefully that shows you the relationship between the concrete and the reinforcement in a reinforced concrete member, and that we are using the best properties of both materials to form a highly efficient and a very popular building component.
So next video we'll discuss some more important points